Hello, and welcome to the ILP webinar. My name is Irina Sigalovsky, and I'm a program director at the MIT Office of Corporate Relations. Today, I'm going to be your host on behalf of MIT's Industrial Liaison Program. As you know, our main objective here is to connect corporations like yours to the relevant resources available at MIT and also MIT connected startups. Today's webinar will focus on digital twins. I'm sure you've been hearing a lot in the last few months how COVID 19 has accelerated digital revolution. What could take years or months now takes months or weeks. The notion of digital twins has been around for a while, of course, perhaps overused because the concept is so attractive. It has become the thing to do, a promised land where one would be able to model and test everything digitally. The realization of this concept has not been easy, however, to say the least. Will COVID 19 change that? Today, we will talk about digital twins, what it is, what its true value and potential is, and what it really takes to develop digitally native production systems. Before I introduce today's speaker, a few notes on logistics. At the bottom of your screen, you have several icons. Please use Q&A button to ask questions and to vote on questions. Actually, you can start submitting questions as soon as the presentation begins because we will break in the middle to take some questions. Please do not use chat to ask questions. Chat is reserved for technical questions, such as if you're having problems with the platform. This session will be recorded, and recording will be available on our website in about a week. With that, let me introduce our speaker, Dr. Brian Anthony. Dr. Anthony is a Director of Programs and Outreach for MIT Nano, Director of MIT's Master of Engineering in Manufacturing program, Co-Director of the Medical Electronic Device Realization Center, and Deputy Director for the MIT Tech Initiative. The focus of Dr. Anthony's research is in computational instrumentation, the design of instruments and techniques to measure and control complex physical systems. The title of his talk today is Digital Twins, the Vision, and Demystified. Brian, over to you.
Thank you very much. And good morning, good evening, good afternoon, depending on where you're joining us from the world. I thank you for joining today and sharing your time and engaging in this conversation. So the talk for today, digital twins, why now, demystified, as I'll try to say, and then a number of examples. And in the good spirit of MIT, some of these examples will be coming to you through the fire hose. Sort of the rate of consuming of information at MIT is often made as a metaphor to drinking from a fire hose. So I'll first introduce you, tongue-in-cheek, to my digital twin. Not a current representation with my facial hair, but does a pretty good job of capturing my facial structure. So not an exact twin, but something analogous. So this is not what we'll be talking about today, but just this is my digital twin. A few visual cues as we go through today. I'll periodically have this big yellow or orange dot, and I'll use that dot to remind myself to stop and to take a question, or in this case, we'll have a poll pop up, and I invite your input and answers to the various polls that we'll have. As well, I think there's a wide range of backgrounds and perspectives on the call today. So I'll have in various places a cloud, a partially transparent cloud, and use that cloud as your cue to, if you're looking for a lot of the details, look through the cloud and get an appreciation for what's partially hidden by the cloud. But if you're just looking for the big picture, feel free to ignore for now what the cloud is partially obstructing. So when we talk about digital twins are a digital version of something physical, and that physical product could be coffee, it could be tea, it could be pharmaceuticals, it could be hand cream, or or water or other enjoyable adult beverages. It could be fiber, could be optical fiber, it could be apparel fiber. It may be an automobile, it may be a wind turbine. It could be more complex, it could be a machine or a process. So a digital twin could be something that we want to emulate and mimic, be a twin of our product or our process, our machine, here a robot, or here a coffee roasting machine, or a stitching machine for sewing together, putting the tag on a tea bag, or for compacting of pills for a pharmaceutical blister pack, or then packaging of those pills, or wrapping the deodorants or water in the plastic film before it's shipped, or filling of bottles, or extruding of fiber, knitting fiber together, or sewing fiber. Depending on your bandwidth, hopefully your bandwidth is pretty good. This is my test slide to see how well the videos are playing. This is a sewing machine, an industrial sewing machine, recorded at 6,000 frames per second, but a real process, a real machine interacting with the real world. Now, if you Google digital twin, you'll find a large number of phenomenal images that try to give this perspective of what a twin is. And you may find things that look like turbines and jet engines, the digital version of the product, where on one side you have the real product, and the other side you have this matrix-like graphical representation. And you'll see that for turbines, or you'll see that for automobiles, or for aircraft, wind turbines, or inside the factory, machines and processes. Here, a wonderful graphical representation of a mixing process. But the digital twinning continues. It goes out to the factory level, the supply chain, the warehouse, the chemical plant, or the logistics operation, or the factory floor, or bringing all of those pieces together. So that was a rapid fire. Here are all these things that are physical that we could think about having a twin for. Now, my first poll, just to get the audience participation going, I'm interested, from your perspective, this is you, you're interested in digital twins of what? Of products, of processes, of machines, sensors, control systems, production lines, factory, supply chains. Pick as many as you would like. Okay, I'm not seeing if we can bring up the poll results. Here we go. Oh, processes, that's fairly high. Product, oh, this is wonderful. So rather uniformly distributed across everything, with a particularly high emphasis on processes and machines. But everything is very well represented. So that's great. And we'll talk about a little bit of all of this today in our rapid fire set of examples. So thank you for that. So let's move on. So physical and digital twins, what does that mean? On the one side, we have all these examples of things that were physical and digital versions of them, these beautiful pictures that are these matrix-like, partially transparent. Clearly, they're done on a computer. What is a digital twin? By other names, it's a cyber object, or a digital avatar, or quite simply, they're models. They are ways to describe the physical world. A digital twin, its value comes in its ability to predict, to understand the current behavior or the predicted behavior of a real physical object. So a digital twin is nothing more than a model. And just to cut through this, I'll say the marketing hype, it's something that we've been doing as engineers and scientists and researchers and product developers and factory floor operators. We've been using twins, we've been using models for our entire career. So let's put that into a framework and how we may think about that. So models can have different forms. They can be derived from first principles, derived from physics. We could write the ideal gas law and model what happens in a chemical reaction. We can write F equals ma, force is equal to sums of masses times acceleration, and start with very basic principles and develop what we say is a white box, full physical knowledge, and be able to write down the equations, or maybe we mathematically code those equations. So white box models, white box digital twins, are derived from physics. On the other extreme, derived completely from data, where we don't have any idea of the real underlying physics, or maybe the physics are too complex really to write down the equations that describe what's going on. And we had to fit, in the language of machine learning and algorithms and data science, we have to fit a model, fit a curve, fit a digital twin to data, or someplace in between, what we'll call a gray box, where we start with some physical knowledge, start with some physical model, and we augment that physical model with data. So what does that actually look like? What are the tools, the things that we use, both from a physics perspective or a data perspective, to develop these digital twins? Maybe back in your engineering days or your or undergraduate days, you remembered developing free body diagrams, and the lumped parameter modeling is a digital twin. I have masses and springs and dampers, and I can connect them together to develop an equation that describes how these things relate. Or I can look at a fluid system and develop a lumped parameter model that has resistance of flow through a pipe and capacitance of fluid being stored in the pipe. So these are digital twins. These are the modeling tools that you use to develop a physics-based, a white box model of some process. If we increase the complexity a little bit, we can use a tool like finite element models, which are really just a bunch of small springs and masses together to simulate where stresses and strains are happening in a complex product. Or adding an additional level of complexity, airflow, computational fluid dynamics that models airflow here around the head of a golf club, or fluid flow inside the mixing of a complex chemical reaction. Those are physics-based, definitely pointing to the white box digital twin model. Now, some of the other modeling tools that we'll touch on today is here a Markov chain, which is really nothing more than representing, if I have a state of the world, in this case, a coin, for example, that is heads. With some probability, when I flip it, it's going to transition from heads to tails, and with some probability, it's going to stay at each flip in its current state. Or a machine, with some probability, will stay operational and running, and with some other probability, will sometimes fail. So we'll use this tool as one way to develop a digital twin. Now, you can't really pick up the New York Times or most academic journals now without hearing something about machine learning and deep learning. So this is a graphical representation of a classic neural net and a sort of a multi-layered neural net. These tools, this neural net tool, is more aligned with the black box fitting of data, where I don't know the physics, I have a bunch of data, and I want to learn, I want to fit my inputs to my outputs. So that's an important concept. Just to sort of level set here, maybe not everything you really need to know you learned in kindergarten about digital twins, but maybe everything you need to know about digital twins you learned in high school, or at least a lot of what you can take away from at least one of the messages from today you did learn in high school. And what do I mean by that? If we have data, in this case, a scatter plot of a system that we've acquired input data for and output data for, where we have a machine, and into the machine we put force, And out of the machine, maybe we get the extrusion rate of a polymer or of a metal. And we plot the inputs and the outputs to the system. And in this system here, it's a bunch of points. I could fit a line. My eye looks at this thing and says, I can fit a line. Now that line that maps roughly my inputs to my outputs, that is a digital twin. It's a very simplistic digital twin. But what we've done is we've found a line. In this case, we've found the slopes and the slope and intercept that best fits the data. We looked at all possible lines. Algorithmically, conceptually, we looked at all possible lines, all slopes and intercepts that describe this line and said, how does it optimally fit? How does it best capture our data? How does it best model? What's the best twin if our assumed model form is the line? How does it best fit our data? And we've done that, and here are my clouds, so you can ignore those if you want some of the high level and just look at a little more deeply if you want to know some of the details. What we've done is we defined a function that we want to minimize. We have our input and output data, and we try to minimize that function, try to find the parameters that minimize the energy, the differences between our model and our data. And for this simple case, we find a slope and an intercept. Now, I have this for a very important reason, because by and large, if we look at any of the other far more complex fitting algorithms like neural nets or autoregressive filtering, most of them, all of them, I would take the extreme statement, if we're looking at gray and black box fitting, are just like line fitting. All we're doing is saying, let's have a complex model that has parameters. For the line, it was slopes and intercepts. And for a convolutional neural net or a neural net, you have weights and biases, and we have our data. And we want to find, through some type of algorithm, some type of optimization routine, the parameters that fit our inputs to our outputs. But in the end, it looks very, very similar conceptually to line fitting. The devil is in the details in terms of the algorithms to find those parameters in a fast and efficient way. So once we have a model, a line or a neural net or something that's physics-based, we take our knowledge, we take our data, we make some assumptions, we try to capture the salient points of those physics or our understanding, build our model, and then use our model. And then we iterate and repeat. The model may not be sufficiently detailed to explain the things that we want or to capture the underlying physics. Okay, with all of that as preamble, why now all of this interest in the air quote version of digital twins? I just told you that you've probably seen everything that I've talked about. You've seen at least advertised what a neural net is. You've seen line fitting. You've seen simple physics to explain forces and masses. You've seen chemical flows. So why now? So here's another poll. Why now all of this interest in digital twins? I'll ask you to pick one. So certainly cloning technology, I have it on my iPhone, so that should be the top of the list, I think. Okay, we'll give it a few more seconds here.
We got a little late start on this, Brian. Maybe let it go a little bit more.
Absolutely. Okay. So our digital twins, are we interested in them now because sensors are so easy to deploy, or video games are driving innovations in the factory? Machine learning is cheap and easy. Digital triplets require quantum computing. It's all about plastics. Okay, so the answer's here. Okay, cloning technology is available as an app, 9%. Okay, so I have some folks on the call that enjoy my sense of humor. Sensors are easy to deploy was second. Machine learning is cheap and easy, that was first. And then way down at the bottom, video games are driving innovations in the factory. Thank you for that. So interesting. So my answers to that, I would actually say equally balanced between sensors are easy to deploy Machine learning is cheap and easy. And what I mean by that is almost video games, the technology behind video games are driving innovations in the factory. So let's be a little more clear on that. So digital twins have existed for a long time, right? They are digital models fed by data that we want to use to predict outcomes. They're not new. The technology that's allowing us to have twins, the same reason that we're seeing that everything is smart or relying on machine learning for a lot of things that we couldn't previously. It's the new technologies that are allowing us to scale things using sensors, using data, using computation. So their twins are not identical. Their value to us comes in their ability to predict something. So our digital twins are building on well-trodden paths, on solid foundations, on existing concepts, but enhanced by new technologies. And those new technologies, sensors everywhere. It can be everything from cameras, which are the background of this slide, to small little miniature sensors that measure distance or gas content or color, or that you can embed into your batches if you're mixing chemicals. The data side, all of our data starts with sensors. So certainly the ability to, in a low cost way, deploy sensors, get data from them, measure things, is revolutionizing our ability to do many things, including making digital twins. Now, learning, the computation, neural nets, some innovations in how we find the parameters. Now, how we do that line fitting, that complex version of line fitting, have allowed neural nets to be more readily deployed. But the gaming industry, or our computers, the graphical processing units, the computation framework, both what you find in your computer, but also the fact that you can go to the cloud, somebody else's computer, and get massive quantities of computation. So those are the new things that are allowing us to take concepts that have been practiced for a long time and put them on steroids to amp them up. So we're going to connect the physical and the digital with data. We're going to learn by using real-world performance to improve our predictions and drive continuous improvement. We're going to use twins, and we're going to use them to design. We're going to use them to predict. We're going to use them to control, operate, and reprove and repeat. And if we have twins, we have models for all aspects of from our product design to product manufacture to product support, then this thing called the digital thread, the digital connection between all aspects of product design, manufacture, delivery, and support starts to emerge. That won't be the main focus of what we talk about today. When we talk about data, there's production data, time series data versus pressure, temperature, gas flow versus time, or velocity and forces versus time, or run charts where we have a process roughly in statistical process control, and we're seeing how it's deviating with respect to the mean. Data also includes event logs or maintenance logs, when equipment is down and when equipment is up. Data also includes sensors, include cameras, the ability to get thermal imagery of molten steel or molten aluminum, or optical imagery of circuit boards or food products. So let's test your knowledge so far, or start at the high level. Let's start at the factory. How do we develop a digital twin of the factory? I may call a company and say, hey, I need help making a digital twin. And I want this graphical representation of my factory, and I want to be able to simulate what's going on. If I peel back the beautiful graphics of this tool, and we'll see some commercial examples here in a moment, what is a factory simulator? The building block, at least at some level that we'll talk about, is an unreliable machine. Every machine, your car, a turbine, a generator, is going to operate for some period of time. It will fail at some point. And we will model this unreliable machine with nothing more than a coin flip. Actually, 2 coins. We're going to model this machine that sometimes goes down by saying, most of the time it's up. It's up, it's up. So I want to flip a biased coin that for the most of the time stays heads. But once in a while, it's going to fail. And a way that I represent this is this thing called a Markov model, Markov chain when we sequence it together. My machine in this case, and I have many machines in my factory, it can be modeled as two states. It can be up or it can be down. And it has some probability of staying up and some probability of going down. And then once it's down, there's going to be a time and a duration associated with repairing it to get it back into its good state. Now we can model that. The digital twin, the underpinning to that is this coin. Take a coin out of your pocket, has to be something other than a Bitcoin, bend it. But bend it, meaning bias it, so that when you flip it a bunch of times, it has the same failure rate as what you observed from your factory floor, where I have this machine that if I look at many instances of time over days and months and years, sometimes it goes down. Let's bias the coin so that I could just flip it, and once in a rare moon, the coin is going to fail. It's going to come up tails. And I'll have a different coin for how long, the rate with which that machine can be repaired. Now, all I'm going to do in looking at these various commercial tools is I'm going to simulate my factory by flipping that coin or bunches of coins for every machine. And I'm going to keep track when a machine is up. If it's up and operatable, material can flow through it. So I'll let material go through. And then I put a glossy, beautiful graphical display on top of it. And I get products called like FlexSim or Factory IO or Siemens Technomatics. But that's the graphical layer on top of just this fundamental ability to flip coins. And what we can do with that coin flipping is we can model a simple production line that has two machines and a buffer between, model each machine with coin flips, keep track of when your coins are up or coins are down, when things are operating, material is flowing through, and I have real production at that instance in time. If one machine is down, I may get an increase in the buffer size between. And it doesn't just stop with one or two machines. I can do this for many machines. I can use this factory simulation notion to figure out different reconfigurations of a factory and what are the impacts of different buffer sizes, or how big should my buffer be. So a factory simulator in this way, it can model production systems, provides this ability to predict what's going to happen with a new layout, consider changes to staffing, to machines, to materials, but building on top of this notion of a biased coin. So in this way, my next question, factory simulation, what type of model is it? Is it a black box model, a gray box model, or a white box model? Are we building on underlying physics? Or do we know nothing about the process? Or is it someplace in between? Okay, so if we can pull up. So gray box. So very few people voted for black box, very few for white box, gray box. I agree. So why is it a gray box and not a black box or a white box? So white box, we're not building on fundamental underlying physics, but we are building on fundamental principle of variability and variation and randomness. So we know there's randomness, we're abstracting away. So we capture some aspects of physics, of some real underlying process, meaning randomness. And we simulate, we run, we flip all these different coins, and we bias those coins based on the data that we have for real machines and real equipment that allow us to perform what if examples and what if case studies. So let's switch paths for just a little bit. That was at the factory scale. Let's use a fiber production through a number of different case studies, if you will, of digital twinning for both materials processing and fiber extrusion. So the digital twins that we're going to consider are going to allow us to look at some very novel ways to make fiber. And that fiber can be fiber that we're putting into our apparel, or that can be fiber that we're embedding into composites. What we're going to consider are optical fibers that are extruding through a draw tower of the type that you would find for optical fiber production, or polymer fibers. And we want to do two things, as we'll see. We want to control the diameter of the fiber, but we don't want to just have a uniform diameter. We want to potentially modulate the fiber, and that gives some interesting properties both optically and physically. And then we also want to embed things, filler materials, inside of the fiber. The machines that we're talking about are everything from a large draw tower, this is a 3-story optical fiber draw tower, or a tabletop polymer extrusion system. And in both of these cases, what we want to do is we want to control the dimension of the product. For an optical fiber, we want to have it be uniform and continuous. For some of the novel apparel fibers, what we want to do is modulate the fiber diameter. And the reason that's interesting is if we have a polymer fiber that we use to then knit or weave our clothing, and we have these sort of nodules along the length, and we then knit or weave them, the fiber, with respect to fibers that cross it, will still roll as it always has, but it won't slide. The knobs on the modulation will stick, and so you can induce very interesting properties of materials that are made out of modulated fibers. But then we also want to embed technology into the fiber. We want to organize materials that are either optical, have optical properties, or electrical properties, or strength bearing properties. Now, the system that we'll start with is this little tabletop fiber extrusion system. It sits about a meter high. It looks just like an optical fiber system. It has a heating chamber to melt the polymer. It has a cooling tank. It has a spooling motor to pull it all through. Now we could start with developing a digital twin for this. We could write down the equations of motion for all the various components. And we could develop a set of equations here, a set of differential equations that we could then simulate in time to predict how this machine is going to respond. If I want to change the set point from a fiber diameter of 100 microns to 200 microns, I may get some overshoot, and that can be modeled by this differential equation going through a physics-based analysis and doing lumped parameter modeling. And if I do that, I can already reveal the fact that this fiber extrusion system is not symmetric. It's easier to, if I want to change the set point of a fiber diameter, it's easier to go from a thick diameter to a thin diameter because I can suddenly pool faster, and it takes more time to go from a thick diameter or a thin diameter up to a thick diameter. So we have different properties, and that's relatively easy to model. But that's a white box model. What are the problems with the model? You know, from your perspective, is it only captures the simple physics? It doesn't account for the part where we have to redo for different set points. It misses random variation, or hey, there's nothing wrong with the model. It's perfect. It'll work.
Slight delay, Brian. Just hold on just for a sec till we get over.
No problem. Okay, so let's see. There's the winner there was misses random variation at 41%. Only captures simple physics. Doesn't account for part where. Must redo for different set points, and then finally, nothing is wrong. It will work. Thank you for sharing. The correct answer is it depends. All of the answers are correct. There's nothing wrong with the model. For some things, it will work. It allows us to predict this sort of asymmetry in how the fiber extrusion process will work. But it's only the simple physics, right? It's the things that we can write down equations for. If we wanted to use this, we would have to redevelop the model when the parts are changing, when there's wear, increased friction. The dynamics could be different for different set points. And without a doubt, we're not capturing the random variation. So how do we capture that random variation? How do we go now from this thing that was a white box model, and we want to instead fit and predict based on real production data. So let's do this data-informed digital twin of our process, where the physical process has material in, parameters in, and real material out, and more data out. And the digital twin that we're trying to find is a mathematical model, some function, or something, a line that takes a set of parameters in for the material, set of parameters in for the settings, and predicts what the material will look like. And we can start to do that by capturing all different types of production data. We can capture in the top row production data when we have a fixed spindle rate of the extruding wheel that's pulling the fiber out of the extrude head. And so we have a nominally fixed diameter. Or we can explore when we are modulating the set points and changing. I want to do for a short period of time a diameter fiber that's around 0.25 millimeters, and then bump it up to half a millimeter, and get all of the data that is the input and the output over many different settings. Now, one way to approach this, I told you that many things look like lines, and I'm not going to lie here. The model that we're going to consider is, we're going to say, let's consider this model. Is it a gray box, a white box, or a black box model, where I have this polynomial form where the y is an output, in this case the diameter of the fiber, and u's are our input, meaning the temperature that we use to melt the polymer, the spin rates of the extrusion system, and there's noise. Now, you could argue that this is a black box model, where I'm just writing an equation down that's trying to relate a series of inputs to a series of outputs weighted with different parameters over time. But the physical intuition that we bring into this, in terms of, well, what are the time delays in our system? Over how many units of time does our input of the history of inputs impact our output? Is it over the last 2 seconds or 3 seconds or 4 seconds? So the lags associated with it inform our selection of this equation, this polynomial equation that relates inputs and outputs. Now, what we have here is our input data, our output data, and what we want to find are these A's and B's, these parameters. Same thing when we did the line fit, the A's and B's that explain our observed data. And if we're able to explain observed data, hopefully we can predict in the future what new outputs will look like for new inputs. Now, here's the big cloud, so feel free to ignore some of the details behind the scenes. But the thing we're trying to find is a set of parameters, our A's and our B's. We have as input our data, our measured fiber diameter over time, and our measured inputs, temperatures, spin rates, velocities over time. And for this particular instance, we've used things called an autoregressive filter, which, if you ignore everything that's behind the cloud for a moment, is nothing more than a line fit. It's using a least squares method, a minimization of energy, to find the parameters, the A's and the B's, that in this simplistic notion looks like a line fit. So then in the end, I have a polynomial, a digital twin, that sufficiently captures my model, my system that is a model. And then I can take my production inputs, which are temperatures, spin rates, and I can run it through this model. In this case, it's these series of polynomials, and predict what's going to happen. And what we're showing here on the plot is our actual measurement of the diameter for this extrusion system versus the predicted response of this extrusion system. So this was a heavily data informed. We did a line fitting, but there is some physical intuition in terms of the structure of this polynomial, and over the period of time that we capture our data to, or our history of inputs to explain our new output. So what we've done here by and large is we captured data, we captured historical data, and we crunched on it, and we found this model. Now, let's continue to talk about the fiber for a moment, but in a slightly different context. So these next several slides are taking that concept of model fitting and amping it up a little bit, where maybe I don't have historical production data, where I can just collect all the data and stop and analyze it and develop the model. But maybe my system is continuously varying. And I want to simultaneously take the inputs and the outputs that I'm getting from my system, but I also, to add a level of complexity, I can control what I want my machine to do. So if I'm trying to develop a model to say, hey, here's the inputs, here's the outputs, what's the best thing that allows those things to be predicted from one from the other? If I also have there a lever to reach into the system and say, what I'm going to do is I'm going to use my least squares, my magical least squares techniques on steroids, but I'm also going to do real-time experiments. I'm going to say, I'm going to look at the uncertainty associated with how well my model is predicting what I'm measuring. I'm getting this data in real time. And I can change my system. I can say, let's go to a new set point or try slight deviations around how it's currently performing. So I can do real-time experiments. So I don't just have to live with the data that I was given from history. I now do this very complex, looks like a line fitting process where I am actively and in real time doing slight perturbations to get more data, better data. But under the hood, it's sort of line fitting, is model fitting, finding coefficients, but where I have the ability to do those real-time experiments. And so we've applied this to things like learning the optimal controller for how to make optical fiber or polymer fiber, where we have our control signals that are going into the machine that produces the fiber. We measure the output properties of the fiber. We measure the input properties of the fiber. We feed it into this neural net, bunch of parameters that we're trying to find that map the inputs to the outputs. But we add this layer of actively saying, hey, let's actually change our new set point. Let's change what our next set of inputs will be. And so in this way, we're able to continuously and more dynamically learn not the underlying physics, but at least a representation of the physics captured through a set of parameters in this complex network of neurons that captures the model of the machine, the model of the materials, and the model of controlled trajectories. And we then use that to then predict and improve our controller. And I'll skip through this slide. I should have had a gray cloud here, but this is really baking and borrowing and stealing from the areas of reinforcement learning, where I have an agent, in this case, the physical machine that's interacting with the world, and I'm actively and dynamically modifying the world to learn, to get more data to learn about the physics of the underlying process. So I ignore the stuff behind this, the cloud, the detail. It's input data, output data, but I'm constantly adjusting those to get the best model parameters that I can. And I know the uncertainties associated with things. And so I can tell the machine to behave in different ways. And in the end, I have a neural net that now, if I look at this complex thing that we're trying to do, which is do this modulated fiber diameter, the plot on the right, the upper right, is showing the modulated diameter control input, or the desired set point, the black line, and superimposed on top of it are various controllers that are either naively implemented, like a PI controller, or learned with this deep reinforcement framework to try to match that desired trajectory of a square wave of modulated fiber. And if we look at the bottom, what's interesting, what that is noting is that we have two dominant input parameters that can change our output diameter. We can pull the fiber faster, or we can push it. And each of those are going to change how material is flowing through. So we've learned in some integrated way in this complex network of weighted coefficients how to sometimes pull the fiber faster, slow down, but at the same time change how we're pushing the input material into the back end of the fiber extrusion system. So this is straight up a black box. We didn't really worry about the physical knowledge other than how to develop a control system. But we constantly are adjusting the set points of our system. It can be small changes or sort of big changes to make sure that we've interrogated a wide space of the physical range of how this machine operates so we can learn a data-informed, a black box model. Something that's often a question here on how we use video in a manufacturing environment. And this takes you away from fiber for a moment, and is a very data-centric view of creating digital twins. So let's look at a couple of processes. Here is a laser weld melt pool. And we would like to have a model for this process that it relates the temperature or the heat going in from laser pulses and how this material is splattering. Or we would like to have a digital model for laser cutting of aluminum. And we would like to try to understand how to control the cut rate and the power rate to not have too much splatter. Or we would like to look at a wire-fed plasma welding process. Again, we have this image data, and we want to use this image data to inform the development of a model to explain our process. We looked at a stitching operation previously. Now here's a binding operation. Now the one example here that I'll use for a couple of slides is, let's see, displays, there we go. This is a diaper packaging line. And we'll notice here the diaper flowing through the line, and there'll be a little bobble at some point. And that bobble will keep going through, and at some point the system will completely jam. So I want to have a digital model that helps me to detect that fault, to predict that fault. What are the things that I can measure from my controllers, or what's the data, what's the information that's embedded in my data from the thing that I'm seeing to try to predict in real time, use this real-time digital model to say, hey, something happened. Our model tells us something's going to really bad happen. Our system's going to jam. How do we approach this as in this framework of digital twins and models? There are many ways. The one way that I'll highlight here is, let's take, for the extreme in simplicity, let's take our data, a video of our process as the digital twin, as the thing we want our process to look like this. Nice, cleanly flowing diapers through our line. And the way that we're going to compare our real physical process to this digital twin is we're going to pretend that we're going to think of our data as a cube of our video as a cube of data. And this cube of data, the model, the yellow, the sort of close to yellow color here, is absolutely a black box digital data only representation of the way that this diaper is flowing through the line. And I have new video coming in. And my model comparison, I develop a comparison engine, a way to say what I really want to do in comparing my digital model to the new data is I want to stretch in time and in space one video cube to look like the other video cube. And once I've done that stretching and compressing, I have this path, this measure of similarity, which is not just, hey, there's a single error at this point in time. It's deviation as a function of time and space. So I have now a model, right, which is really just a video of my example process. I have new data, new sort of possible models coming in of my process under test or under operation. And I compare those two in real time to make process control decisions. And we developed algorithms that allow you to do that video comparison in real time, where real time is thousands of frames per second. And this is what the sort of overall sort of framework looks like. I have my model, I have my new data coming in, I do a real-time comparison, which is a little bit more complex now than just line fitting. But what I'm doing is finding this time-space path of our model through my new incoming data. That time-space path tells me something about the spatial similarity, temporal similarity, or overall sort of trajectory similarity. And the only reason that I can do this, when I'm taking a high-speed camera that's spewing data at me at gigabytes, 10s, 20s, 30s of gigabytes per second, is because I have the camera that allows me, the sensor that allows me to do that. And I have the benefit of video gaming, GPUs that allow me to massively parallelize the processing of my video streams. And I take my model and I process it, compare it to my new incoming streams. And in the end, though, I extract my model comparison from that model. I extract parameters that say something about spatial similarity, temporal similarity, and I can map out as a run chart the difference between my model and new incoming data. And what we're seeing here, the big thing to point out, is where we had that little bobble in the video. If it came through at cycle N, a little bobble was detected through a real-time comparison of my model to my new incoming data. And I can stop the machine before I get out here to the later cycle where things are completely jammed and stopped. Okay. So I think with that, let me just go to my few wrap-up slides here. Okay. So what I wanted to convey today is that digital twins, there's nothing magical about this notion of a digital twin. It's a model that can be informed by physics. It can be informed by data. You can develop models for products, for processes, for machines, for factories, and you use them to design, use them to control and predict. And the real sort of holy grail, if you want to call it that, sort of one of the big opportunities, certainly in this COVID era, but just in general, is how do we use them? If we then take, how do we use them in an integrated fashion? If we take all of these digital models together and we have models of process, models of factory flow, models of machines going up and down, and we incorporate them, that's not a solved and done problem. But if we're able to tie them together at various scales, you can imagine, and there are certainly commercial attempts to start to do this, having a full, from low resolution to high resolution, small time to big time, virtual representation of my entire process, which could potentially allow me to do virtual commissioning, that could allow me in this era of needing a lot more masks, N95 masks, say, hey, I want to develop a new mask line. I have all the data from an existing line. How do I go about making it faster or making it easy to build a new line to meet the demand, for example, for personal protective gear? Okay, so thank you for that. I also want to thank you to my students and postdocs and collaborators, David Kim, Song Woon, Lauren Fidrani, John Du, and Dave Hart, whose work is partially represented through all of these slides. And I welcome some questions, and I thank you for your time.
Brian, thank you very much. We actually have a number of very good questions and a few minutes to address them. So first question, what competencies would a company need to develop in-house to effectively use digital twin capabilities?
That's a great question. And there is not a single competency. I think the important thing to note when you're applying machine learning in a manufacturing environment is that you need both the physical intuition, people that know the processes, that know the physics, that have an intuition for the physics, and the people that know the data science. And you need to have an appreciation of the language of data science, and a language for the appreciation of the language of the factory floor. And so the competencies, you need that team that has a joint data perspective and a physical perspective. And I'll take the opportunity for that question to add one other thing. One of the big differences often in data science applied to a manufacturing environment, when you're talking to the data scientists that you want to get into the factory floor working with you, is that there often is not a lot of bad data. When you're doing good production and you're making quality product, you have a lot of good examples. And often you have very few bad examples of how things are failing. So one of the, I'd say, in most machine learning, in many machine learning approaches, you want to have a balance between good data and bad data. And so one of the reasons that it's important to get your head wrapped around both white box and gray box modeling is that you should not really be just using black box modeling in the manufacturing environment. You don't have enough data that's good and bad. You need to incorporate some of that physical intuition and have that sort of engineered factory floor perspective and the data science perspective. So long-winded answer to the question, Irina.
But that was a great insight. Can you talk about how the dangers of inaccurate digital twin replicas, risks of misrepresenting systems, differing realities of replicating objects, and inaccuracies of the process replications have been tackled?
Yeah, so the models are only going to be as good as either the physics that you've informed them with or the data they've been presented with. You're always going to want to collect more data to continue to validate that the model is working sufficiently for your purposes. And you're going to be constrained in the types of questions that you can ask based on how much you can capture. So a white box model, the benefit of a white box model is that I can, with a sort of robust physics understanding, make big changes to what the model can potentially predict and get sort of big trends. With a data informed model, it's only going to capture the operating conditions and the process conditions that it observed. And so it's having that ability to continually train. It doesn't have to be in real time, continually update, and just to be cautious that you understand the assumptions that you made in forming the model and the data that you use, the implicit assumptions that were embedded in the data that you used to develop the model.
Yeah. Next question. Are digital twins applicable to computing infrastructure, such as data centers or hybrid cloud designs?
Certainly. It's if you look at them, sort of the data center as a factory that has resources that are consumed for air conditioning and power distribution, that's at least one level. And some machines are going to go down. The servers are going to go down. A rack is going to go down. And so at that level, absolutely, is looking at the factory, sort of the factory models of machines up and machines down. And if you look at the flow of information as well, it's maybe less, the models for how data is communicated is far more natively digital in its physical form. And so there are maybe less complexities looking if you're trying to model how data is flowing. But managing data centers and managing that infrastructure, that's a factory. That's a factory that's moving information and power around to help manage that energy. And so modeling that is certainly applicable with some of these tools.
Question from the audience, but also something I wanted to ask. What industry is more advanced in terms of adopting digital twins, and why?
Oh, that's a great question. I'd say every industry is using them in some way, and we always have. We've as engineers and scientists and factory floor workers, we've been using a model, sometimes simplistically, and so it's every place. The question is, what are the ones that are really benefiting from the new innovations in sensors, the new innovations in computation? Certainly, the electromechanical industries, making of everything from phones to cars. Pharmaceuticals, yes, maybe not as much so. Chemical processing, there is definitely there's not a singular industry that I'd say is a clear leader. But that means that I would also say there's not a clear industry that has sort of solved the problem of the full digital commissioning. So I think in every industry, it's still relatively early days in terms of what is possible. But all the hype, all this excitement, and I shouldn't maybe call it hype, but all this excitement about the digital twins, it's now achievable. You need the competencies in your organization to solve the problems, to do the data science, to understand the factory floor and the processes. But the tools are available, the sensors are available, the computation is available, and there are companies, both small and large, that are rampantly scampering to provide those functionalities. But it's a large communal learning effort to scale them up to what is potentially achievable for multiple scales in time and in space.
So we have many, many good questions, but unfortunately, very unfortunately, we have to stop here. Brian, thank you so much. And to the audience, I hope you found today's presentation informative and relevant, and we would love to hear your feedback. And with that, please stay safe and healthy, and goodbye.
Thank you very much. Have a good day.